Hello everyone, Assalamu alaikum. Welcome to our second lecture on aeroelasticity. Today we will discuss about aileron reversal speed. This math I'll be showing you today is from the Mekson's book, and it has the relevance to the previous math we have done. We will also discuss about aileron reversal speed, like when do we have aileron reversal speed. Then we will move on to the numerical problem. How does an aileron work? Aileron is basically one device, you can say. It's attached to the wing, and what it does, it creates differential of lift on both wings. It means we will have more lift in one wing and we'll have less lift on the other wing. Therefore we'll have a roll, right? So basically the purpose of aileron is to produce roll. Like if you want to roll an aircraft, you will need an aileron. This is as simple as that. Okay, if you see this picture here, we are trying to roll ourselves to the left, right? That means we need to have more lift on this right wing, and we have to have less wing on the left wing. As you can see here, our aileron is deflected downwards, and here our aileron is deflected upwards, right? Hence we have this differential of lift on both wing. So if we take only the cross section of aileron with a downward deflection, it looks like that. Basically, if we have an undeflected aileron, as you can see, this velocity is the free stream velocity. Because we have deflected the aileron, our angle of attack has increased, right? And hence we'll have an increment of lift, right? That means this delta L is due to the deflection of the aileron, and therefore we will have a positive nose up moment, right? Because if we have a increment in the lift, we will have a increment in the moment as well. However, this particular case is only valid for the rigid wing. When we're talking about the aeroelastic phenomenon, in that case we have to consider the elastic nature of aircraft. For example, our wing is elastic, our whole aircraft is elastic. Due to different kind of load, it will bend, it will twist, and so on and so forth. So elasticity of an aircraft comes when we have a higher velocity. Generally what happens is, like, because of this aileron, for example, we have a twist center here because of the hinge, and we have a lift here, right? So this lift, we are calling it delta L, and if we try to move this lift force to the elastic axis, we'll actually have a nose down pitching moment, right? We'll have a nose down tendency. The overall lift will be decreased, even though we have produced a increment in lift. As you can see here, our lift is here, this L, and we're moving this force to our elastic axis. In that case, our moment will be in this direction. We'll have a positive nose up. This is nose up, right? And this, if we were considering the aeroelastic problem, in that case this delta L will create a nose down tendency, because as you can see, the moment is in the negative direction. This is how the increment of lift due to aileron deflection can reduce the overall lift. At a certain speed, the aileron effective does. That means the aileron is supposed to create lift and produce lift, but it will produce less lift, and at a certain speed it will become zero. That means this delta L will be equal to L. So there will be no lift produced by the aileron, and effectiveness of the aileron will be reduced. It will not do what it's supposed to do. And if we go beyond that, when delta L is greater than L, in that case, if we go beyond that, our aileron will do the opposite it is supposed to do, right? At delta L is greater than L, in that case, what will happen? We'll have nose down pitching moment. In this phenomenon, when our aileron effectiveness is 0, we call it the critical aileron effective speed. I hope you understood this far, and now we'll go to the math. Okay, this problem is from the Megson's book and is related with the previous one. Calculate the aileron reversal speed corresponding to the minimum required torsional stiffness for the wing of example 28.1. Okay, so as you can see here, our minimum required torsional stiffness for the wing. That means, and as you can see, the parameter of the wing is given in the previous math. We have to extract those data from there as well. Now we need to determine the aileron effectiveness. How effective our aileron at a certain speed, right? The aileron effectiveness at a speed of 150 meter per second. The rate of change of lift coefficient is given, and also the rate of change of pitching moment is also given due to the aileron deflection. As you can see, it's given negative, right? Why? Because we're calculating the aileron effectiveness and our moment will be reduced. Okay, if we deflect our aileron. Now we are going to extract all the data we have from the previous math, also from here, this map, particular map. Okay, this speed 150 is really crucial for the second part of the map. Okay, and these are given. And as you can see, this beautiful equation we have found from the offline class, so I'm not going to derive that. But however, you can see this K is the stiffness, torsional stiffness, and is a negative because why? We have another negative term here which will be cancelled out. And then we have rho S, C is the part. As you can see, we do not need EC here. We just only need the length of the cord. We do not need the E. Is the distance between aerodynamic center and the flexural center. The distance between those two is called EC, right? And we have, as you can see, change of lift due to aileron deflection, change of moment coefficient due to aileron deflection, and this A is the lift slope curve. Every values are given in the question. So you just need to put the values there and you have to find out the velocity. Okay. And aileron effectiveness, how do you calculate that? Using this particular equation, where this V is equal 150. This is given because at this particular point we want to see if our aileron is effective or not, right? VR is the aileron reversal speed. We need to find out this one from the previous equation. Using previous equation, we need to find this particular value, and this V is 150 and this VD is 200. It's given in the math, right? Okay, these are the given data and we just need to input those values. Let me help you with this inputting those values. K is this one, it's K. Let's put this value here. Change in lift coefficient due to aileron deflection, right? This one is, we have 0.8, and this big term here, that is negative minus 0.25. Then this is given, which one is this one? So it's given 3.5, and we have rho is given 1.226, S is given, and C is also given, right? C is the port, and wing area is 330. Okay, so put those values and you get a beautiful answer. Okay, as you can see, we have speed at 178.8 meter per second, and we have a divergence speed at 200 meters per second, right? This is given, right? And as you can see, particularly in this problem, first we will face the aileron reversal problem, then we will face divergence problem. Now we have to input those values here and we'll get this answer. So this answer, you can write it down in a coefficient form or you can write it down in a percentage form. Both of them are okay. No need to worry, you just do that. Hopefully you'll be able to answer this type of problem if it comes to the exam, and I wish you all the best for your exam. Thank you very much.